All right, moving on to question 11 on the math subject GRE practice test. I really like this question. I think it's kind of fun. We're given this function with the restricted domain and asked essentially, is it one-to-one and onto? And if so, what's its inverse? What I think is cool about this problem is there's lots of different ways you can solve it. There's kind of a standard way to solve it that you'd see in a textbook that works perfectly fine. It's a little bit interesting algebraically, I guess. But there's also several tricks that if you're a little bit clever can save you a lot of time, which I really appreciate. So anyways, our function f of x is x squared plus 6x plus 1. So you're thinking it kind of looks like our standard parabola opening upward, but it's shifted either up or down and left or right. And we're not considering the entire parabola, we're restricting the domain to only include numbers from -3 to infinity. So let's start with a and b. We want to figure out if this function is one-to-one and if this function is onto. Lots of ways to do that. I think the way that makes the most intuitive sense is just to get an idea of what this graph looks like. And maybe you're like, yeah, but I don't have a graphing calculator. That's okay, we can graph this function fairly easily. The sort of standard way to do it is using this method called completing the square. So I take this function, f of x equals x squared plus 6x plus 1, and my goal is to rewrite this as x plus or minus something squared plus or minus something. The way I'm going to do that is I'm going to recognize a perfect square on the right side of the equation. And you're like, that's not going to work. I don't have a perfect square right here. X squared plus 6x plus 1 is not a perfect square. X squared plus 6x plus 9 would be a perfect square, but I don't have x squared plus 6x plus 9. That's okay. We can make this x squared plus 6x plus 9 by just adding 8 to both sides of the equation. Or if you don't want to add to an f of x, add 8 and then subtract 8 so that you're not changing the original function. Whatever. The reason we did that is now we have our perfect square. X squared plus 6x plus 9 is just x plus 3 squared. So my original function can be rewritten as x plus 3 squared minus 8. In case you struggle to make this a perfect square, in the case where your leading coefficient is a 1, you just need to make this number half of this number squared. So if we let a represent the leading coefficient, 1 in this case, and b represent the linear coefficient, 6 in this case, and c represent the constant term, in the case where your leading coefficient is 1, the way you'll get a perfect square is by making this number b over 2 squared. 6 over 2 squared in this case. If you're taking this test, you're probably pretty comfortable recognizing that x squared plus 6x plus 9 is equal to x plus 3 squared. But just FYI, you can kind of shortcut this. This will always be x plus b over 2 squared. Anyways, we've rewritten our original function in this new form. Why did I want to write it in this form? Because this form is conducive to graphing. I can think about this as just a transformation of my standard parabola y equals x squared. I know y equals x squared has a vertex at 0, 0, and goes through 1, 1, and 2, 4, and -1, 1, and -2, 4. And then I know that this minus 8 right here is a vertical transformation, so it shifts my graph down 8 units. And this 3 is a horizontal transformation, so it shifts my graph left 3 units. You might think this should shift it right 3 units, but horizontal transformations are kind of always the opposite of what you'd think. So this point that was at 0, 0 is going to end up over at -3, -8. And if I shift all the other points on this graph accordingly, my graph ends up looking something like this. But remember, we're not interested in the entire parabola. We're restricting the domain to only include numbers from -3 to infinity. So what that means is we only want points on the graph to the right of this dotted line. We're only considering this part of the graph. If you stare at that purple part of the graph, hopefully you can answer these questions. First, is it one-to-one? A graph is one-to-one if it passes the horizontal line test. To fail the horizontal line test, you need to be able to draw a horizontal line that intersects your graph in more than one spot. Can you do it? No, you can't. Any horizontal line that you draw will intersect the purple part of this graph at most one point. Therefore, the purple part of this graph passes the horizontal line test. Therefore, the function is one-to-one, so A is a false statement. Is the function onto? A function's onto if the range is the same as the codomain. I think I have all that vocabulary right. If it's possible to get any number from -8 to infinity, including -8, out of this function with this restriction. Well, once you have the graph, that's fairly obvious. The fact that this vertex here has a y-coordinate of -8, and it increases infinitely to the right, tells us that the range of this function includes all numbers from -8 to infinity. This function is onto, so saying that it's not onto is a false statement. Now that we know it's one-to-one and onto, all we're asked to do is figure out its inverse. The standard way to figure out the inverse is to take the function and sort of change the f of x into an x and change all the x's into y's. Why do you do that? Because the inverse function sort of switches the inputs and the outputs. X is the letter I use for the input, y is the letter I use for the outputs. So I switch those, and then I solve this equation for y. Unfortunately, this is a hard equation to solve for y because I have multiple y's over here, one quadratic, one linear. Fortunately, the trick for solving this equation is something we've already done. It's this completing the square trick again. Rather than switch the x's and the y's in this form of the function, we should switch the x's and the y's in this form of the function and get that x is equal to y plus 3 squared minus 8. Solve this equation for y and you got the inverse. Because I've only written the letter y one time, this is pretty easy to solve for y. Add 8 to both sides, I got x plus 8 is equal to y plus 3 squared. Take the square root of both sides of the equation. When you do that, you should put in a plus or minus. However, because of this restriction on the domain, we're considering the right half of this upward facing parabola. And what that means is we want the top half of a sideways facing parabola when we're considering the inverse. I know that because another interpretation of the inverse, equivalent to switching the x's and the y's, is reflecting over the line y equals x. And if you reflected this purple part of the graph over this line, you'd end up with something kind of sort of like this. Top half of this sideways parabola means I want the positive value here. If I restricted the domain to be negative infinity to negative 3, I'd be looking at this side of the parabola, and if I flip that over this line, it would give me the bottom half of this sideways facing parabola, in which case I'd want the negative solution here. Anyways, subtract 3 from both sides, and we got y equals negative 3 plus the square root of x plus 8. Go up to the answers, we see that written right here. What that means is that E is the correct answer. What we've just done is sort of the by-the-book method of solving this problem. And it's great, it works, and if you're pretty good with algebra, you could probably hammer it out in a minute or two. But as I mentioned at the start of this video, there's several shortcuts that you can do. If you recognize that this function is just a transformation of the standard parabola, and you're thinking about whether it's going to be one-to-one or not, whether it's going to pass the horizontal line test, really what it comes down to is, which side of the vertex does your domain start or end on? We restricted the domain to start right at the vertex here, which makes this function one-to-one. If we started to the right of the vertex, so like, I don't know, x equals negative 2 or something, and restricted our domain from negative 2 to infinity, we'd still be one-to-one. We'd just be considering this portion of the parabola. But if we started to the left of this vertex negative 3, like negative 4, well now all of a sudden we're in trouble. Because now this part is our graph. I've drawn over this thing so many times you probably can't even tell. And it no longer passes the horizontal line test, right? I can draw a horizontal line that intersects my graph in more than one spot. I know this isn't really horizontal, but it's as close as I can draw. Anyways, the point that I'm trying to make is to answer the question of whether or not this function is one-to-one or not, really all we need to know is where is the vertex of this function. A handy little trick is that the x-coordinate of the vertex of any parabola is always equal to negative b divided by 2a. So all this work that we did, completing the square and recognizing the function transformations, which is great knowledge to have, served you really well in a different problem, ends up not being totally necessary. We could look at this original function and recognize that a equals 1, b equals 6, and c equals 1, and just go plugging that into this formula to get negative 6 divided by 2 times 1. In other words, negative 3 is the x-coordinate of the vertex. If we know we're restricting our domain to start at the vertex and go in either direction, we know our function's going to be one-to-one. And you're like, yeah, what about the onto part? Well, if you're really strong conceptually, you can answer that without graphing also. First, because a is a positive number here, we know this parabola is going to open upwards. So really all we need to know is the y-coordinate of the vertex negative 8? Because if the y-coordinate of the vertex is negative 8, we know our domain includes the vertex and all numbers to the right of it, so that means our range includes the y-coordinate of the vertex and all numbers greater than it. And you're like, okay, cool, what's the formula for the y-coordinate of the vertex? Well, there is a formula, but it's not as easy as this one. I think the easiest way to do it is just say that the y-coordinate of the vertex is f of negative b over 2a. Right, you want to know the y-coordinate of the vertex, just figure out the x-coordinate of the vertex and plug it into your function. So in this case, f of negative 3 would be equal to negative 3 squared plus 6 times negative 3 plus 1. What's that, 9 minus 18 plus 1? Sounds a lot like negative 8. Without graphing and completing the square, I've recognized that my function is being restricted to include all numbers to the right of the vertex, and I know that my vertex is at negative 3, negative 8, therefore I know that my function is one-to-one, and I know that my function is onto. And you're like, yeah, that's all great, but I still need to know what the inverse function is. And remember, to find the inverse down here, what we did is take advantage of our work that we did completing the square, right? We started here, kind of. Yeah, that's true, and if you want to know the inverse function, this is probably the best way to figure it out. However, you don't need to know the inverse function. You just need to choose which of these three is the inverse function. And if you know that all an inverse function does is switch inputs and outputs, all you gotta do is find an input-output pair from this function, switch the inputs and the outputs, and see if they work over here. What I'm saying is if I take this function and I plug 0 into it, for example, just because that makes my math as easy as possible. 0 squared plus 6 times 0 plus 1 is equal to 1. I know that when I put 0 into this function f, 1 comes out. What that means is that 1 comma 0 must be on the graph of f inverse. So I can just check which of these three functions satisfies that restriction. If I change all the x's into 1s here, will 0 come out? No, because 36 plus 1 is 37, and the square root of 37 is some crazy decimal, and 6 minus some crazy decimal is not going to be equal to 0. This is not my inverse function. What about this one? It's even worse. Plug 1 in, you get 37. Root 37 is some number slightly bigger than 6. 6 plus some number a little bit bigger than 6 is 12 and change. Certainly not equal to 0. That's certainly not my inverse function. What about this one? Change all the x's into 1s. 8 plus 1 is 9. The square root of 9 is 3. Negative 3 plus 3 is equal to 0. Nice. That doesn't necessarily tell me that this is the inverse. It just doesn't allow me to eliminate this from the possible inverses looking at this one single point. But because I've already eliminated these two and it's a multiple choice test, I know this is my answer. What if you got really unlucky? What if 1, 0 happened to satisfy this equation and this equation? No problem, just find another pair. Figure out f of, 1. Sure, f of 1 would be 1 squared plus 6 times 1 plus 1. In other words, 8. Plug 8 into these three equations, see which ones it satisfies. I'll leave the math to you, but what you'll see is, again, it doesn't satisfy this one, doesn't satisfy this one, but it is going to work down here, right? 8 plus 8 is 16. The square root of 16 is 4. Negative 3 plus 4 is equal to 1.